Hey guys, today we are going to be talking about section 3.4 from our textbook, which is kind of a nice merging of almost all the other subjects than chapter 3 that we've talked about so far. So 3.4 is about something called linear programming. And what it is it's a strategy based on constraints, assuming that, maybe in real world situations, we don't have unlimited money, we don't have unlimited time. So there are some constraints, but we want to optimize something. So when is it used? I'm going to start filling this out. It's used whenever we're trying to optimize some quantity. And by optimize, that typically means find either a minimum or a maximum value. Optimize means find the optimal, the best solution. And most of the time, if you're a company and you're trying to figure out profit, you want to maximize profit. Or if you're trying to keep costs low, you want to minimize costs. And so typically that min or that max is going to be the optimal solution, and that's what we try to find when we are using linear programming. Now, a couple other pieces of vocab, and then we'll dive right into the problems. The solution to the system that we talked about in 3.3 when we graphed inequalities. Well, the solution to the system is still a solution, but in linear programming, it's often called this feasible region. Feasible means kind of possible, doable. So based on the constraints we have, is this a doable solution? And if it is, it falls within the feasible region. So wherever we shade for all our inequalities, that is our feasible region. It can be bounded, meaning completely enclosed, or it could be unbounded. Let's say that we're trying to calculate costs and hopefully minimize them. Well, there's a situation where we could just keep buying and buying and buying and go further and further into debt. That would probably not be the best situation, but there's no bound on how much money and loans we take out and debt we accrue. So that could be an unbounded, and we'll see an example of that. The vertices, as you see right here, are the corners of the feasible region, kind of like geometry, where the vertices were the corners of a polygon. And so that brings us to kind of probably the most important thing on this page. Anytime you see something with fundamental theorem in the title, it's probably really important. So fundamental theorem of linear programming says that if a min or a maximum value exists of a bounded region, then it has to exist at one of the vertices of the feasible region. So let me break this down for just 1 second. We already said that we're looking for mins and maxes. So if the thing we're looking for exists of a bounded region, then it has to exist at one of the vertices. Now, this is actually really good news for us. And here's why. I'm going to make a quick sketch over here on the side. Let's say we graph something, and let's say we find that our feasible region is right here. And these are all the places we can be to satisfy our constraints. Well, instead of having to test every single point in that region to find the min or the max, what this fundamental theorem says is you only have to test 3 points, because the min or the max will be on one of those 3 vertices. And so this fundamental theorem actually saves us a ton of time. We don't need to test anything inside. We don't need to test anything else on the edges, just those 3 vertices. So let's dive in and see what this looks like in a problem. So here's the example. It says find the max and min values of the function below and where they appear. Now notice this isn't a real world problem yet. We haven't been given any context, but we're given 3 constraints, and then we're given this f of x and y, f of x comma y. Now this right here is something that's called our objective function. At the end of the day, that's what I'm trying to minimize or maximize. It's my objective, to find the optimal solution for that function. So I'm going to hold on to that for now. I'm not going to do anything with it. And I'm going to start by graphing these constraints. So x is less than or equal to 5 means I need a vertical line. It's an x equals. So a vertical line at 5. I'll make it solid because it was less than or equals. And I know I need to shade less than or equal to this line. I'm going to do what I showed kind of at the end of that 3.3 video. And I'm just gonna, to make my graph not get cluttered up with scribbles and shading, I'm gonna say I know I'm gonna shade to the left because this x is less than or equal to, and I will shade to the left, just not yet. Let's continue on. Y is less than or equal to 4. That's a constant function. So I'm coming up here and gonna draw myself a horizontal line at y equals 4. So that's my y equals 4, and I wanted to shade y is less than or equal to, so I'll draw some arrows below saying when the time comes, I'll be shading below here. And so we can see already just from these two constraints what is possible for our feasible region so far. It's that bottom left area where it's shaded by both blue and red. But we got one more. X plus y is greater than or equal to 2. I'm going to put that in slope-intercept form. Y is greater than or equal to negative x plus 2. So plus 2, slope of negative 1 because it was negative x. Grab my ruler. I'm going to draw that in. And almost. There we go. That looks pretty good. And then y was greater than or equal to this magenta line. So I need to draw little arrows above it because I will be shading above because it's a greater than or equal to. So step 1 with linear programming problems is just graph the thing. Graph and find your feasible region. Now, where would we shade for all three of these? Below blue, left of red, but above magenta purple. This right here looks like our feasible region. This triangle. So this triangle is my feasible region. What are we working towards right now? We are working towards finding the max and the min values of the objective function. And here's where we're going to pull out that fundamental theorem of linear programming, which says we have our feasible region, we know we're looking for max and min, we don't have to test everything. The only points we have to test are here, here, and here. We have a bounded region, it's completely enclosed, and so all we need to be concerned with are these vertices. It looks like this one's negative 2, 4, looks like 5, 4, and 5, negative 3, I believe, just looking at the graph. So how do we test these then? Kind of the last step is, now that we have our vertices and we know what we need to test, we're going to make a table. I'm going to say x, y. That'll be the left-hand part of my table, and I'm going to list out my 3 vertices. Forgot a comma in there, negative 2, 4, 5, 4, and 5, negative 3. So listing out all of the vertices, the corners of my feasible region. Now what about my objective function? That's going to be the right-hand side. So f of x, y, which was equal to 3x minus 2y. And I'm just going to plug in my x and y values. So 3 times negative 2 minus 2 times 4, plugging in the x and y coordinates from that vertex, equals negative 6 minus 8, it looks like, not 10. 2 times 4 is 8. So negative 6 minus 8 equals negative 14 is what it appears. So the value of the objective function at that vertex is negative 14. Is that the max? Maybe. Could just be a really low max. Is that the min? Possibly. Let's plug in our other ones. So 3, I'm going to just color code. So 3 times 5 minus 2 times 4. So 3 times 5 is 15 minus 8 equals 7. Okay, so maybe that's the max. And then finally, my third vertex, I'm plugging in that x coordinate, that y coordinate. 3 times 5 was x, minus 2 times negative 3 would be 15 plus 6, it looks like, because of the negative 2 times the negative 3. 21. So I said that the table was the last step. It basically is all that's left is for us to evaluate and find our answer. What was the maximum objective function? It looks like it's 21. So the max equals 21. And then the problem also asked us in those parentheses, find the maximum values and where they appear. So where did we get 21? At 5, -3. So a lot of times I like just drawing at 5, -3. And then what about my min value? My min value was -14, it looks like. -2, 4 got us -14, so that is the min value. And it happened at -2, 4. And there's our answer for this linear programming problem. So multiple steps for sure. Graph your constraints. Graph your constraints shade, find your feasible region, find the coordinates of those vertices, and then use a table to plug them into the objective function and see which one gives you your highest max value and your lowest min value. So that is a really good kind of standard example of linear programming. We got 2 more to do. So here's the next one. Same instructions, basically find the max and min values and where they exist. And so once again, we have our 3 constraints, and then we have our objective function. So I'm going to start by graphing my constraints. I'm going to get this into slope-intercept form. So y is greater than or equal to -2x plus 3. So plus 3, -2 is my slope, so down 2 over 1. Grab the ruler. And right about maybe a little bit less. Okay, that looks pretty good. It's greater than or equal to, so solid line. And I need to be shading above this line when the time comes. So I'm going to draw my little arrows, just reminding me y is greater than or equal to this line. All right, next one. So 3y, if I move the x over, is less than or equal to x plus 9. Which means that y is less than or equal to 1/3 x plus 3 if I divide everything by 3. So plus 3. And I'm looking for 1/3 x. So up 1 over 3 gets me right there. Draw my line in for 1/3 x plus 3. If I can get this lined up pretty well. That looks pretty decent. Maybe a little bit more. We do want our graphs to be pretty precise because that's where we're going to be finding our coordinates from a lot of the time. So draw this one in. And we've got y is less than or equal to. So I know I need to shade below. All right. Last one, I'll do this in magenta, and it's y is less than or equal to -2x plus 10. So plus 10, okay. Plus 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I clearly didn't make my graph large enough. Down 2 over 1. I'm going to intrude on that previous problem a little bit, but the graph should look something like this. Okay. And I'm looking at this and I realize in my graphing, you might have caught this already. I'm going to fix it really quick. I made a mistake on my red. -2x plus 3 was the function, but what did I do? I just miscounted my 3. Little embarrassing. If you notice, I made that y-intercept 4. So let me fix that really quickly. That will happen. So let me get, hopefully, here we go. It'll be purple, but that's okay. And let me move it right here. And that was 3, so I think I should be right there. Okay. Actually, Yeah, we'll just leave it. So red, we said was negative 2x plus 3. My graph was looking a little funny. That's why I spotted that. So make sure you're counting correctly when you plot these on your graph. All right, and I think I missed some arrows. I needed to be greater than this red line, and I needed to be less than or equal to this magenta line. So where is the region that satisfies all of my constraints? Well, it's this region below blue and kind of in between red and magenta. And you guys can see kind of what makes this one different is that this is not a bounded region. This goes down and down and down and down and down, and it could keep going down forever. There's no boundary on that bottom side. So I like to just analyze these anyway. I know the fundamental theorem said, okay, we can't necessarily find a max and a min, but this is 0, 3. This is 3, 4. So I like to make my table anyways, and I'll show you why here in a second. X, y. We had 0, 3. We had 3, 4. And then my objective function, which was f of x, y, equals 5x plus 4y. Let's see what happens if we plug these points in. So 5 times something plus 4 times something. And I'll kind of just set that up in my green pen while I have it out. And I'm plugging in 0, 3 in the first row and 3, 4 in my second row. 0 plus 12, looks like this one gets me 12. 15 plus 16, looks like this one gets me 31 overall. But I'm not gonna say that's my max and my min, because that's kind of just not true. I could go down forever. The question is, as I keep going down, are my values for my objective function getting larger or smaller? So here's what I'm gonna do. A little bit off the books. The book doesn't really cover this, but I like doing it. I'm gonna pick a point somewhere inside down this bounded region, and I'm just gonna pick, say, 3, 1. I know that's not one of my vertices. But 3, 1, if I plug that into my objective function, it looks like I will get 15 plus 4, which equals 19. Okay. And then I'll do one more. I'll do maybe 5, 1, 2, 3, 4, 5, comma, negative 2. So 5, comma, negative 2, I'm going to plug in, and I'm just plugging in to see what is happening to my objective function as I go down. 5, comma, negative 2. 5 of that plus 4 of that equals 25 plus negative 8, so minus 8 is 17. So it looks like as I go down further and further, I'm kind of dropping. I went from 19 to 17. I could probably plug something else in, and I'll do that really quick. 6, comma, 1, 2, 3, 4, 5. 6, comma, negative 5. And again, all this in red is me just trying to see what is the pattern, what is happening here. Because if I plug in 6, negative 5, I'm hoping it gets even lower, because then I found my pattern. 30 plus negative 20 is just 10. It keeps going down. So here's what that allows me to say. I think I found my max value earlier. My max value is 31. And it happens at 3, 4. And then I can say that there's no minimum value because, excuse me, by looking at the graph and trying a few of those points, I see every time I kept going down, 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 well, my objective function went down, down, down. It went from 19 to 17 to 10, which means that it can keep doing that forever and ever, and we'll never have a minimum value because we can always go lower. So This is what I like to look at for unbounded regions. You won't see too many of these, but if you do, try a few of those points as you go down and see what the pattern is to see if you keep going lower. And so with the objective function, you have no minimum, or sometimes the objective function as you go down will actually increase and then you'll have no maximum. Okay, so kind of a crazy example there. Last problem of the day, I wanted to give you one that's a little more word problem-y. And so here's what that looks like. A landscaping company has crews who mow lawns, prune shrubbery. The company schedules 1 hour for mowing jobs and 3 hours for pruning jobs. I'm going to start annotating this a little bit. 1 hour for mowing jobs, 3 hours for pruning jobs. Each crew is scheduled for no more than 2 pruning jobs per day. Each crew schedule is set up for a maximum of 9 hours per day. On average, the charge for mowing a lawn is $40 and pruning shrubbery is $120, and we need to find the combination that we should schedule our work crews to maximize the income, maximize the amount of money we get. So what are we doing here? Well, I'm looking at this and I'm saying, it looks like there are 2 things we're trying to figure out. We're trying to figure out maybe M equals hours of mowing, because the 2 things they kept talking about were mowing and pruning shrubbery. So I'll make P hours pruning. This problem's way harder because we have to actually write out our variables and our constraints. Now, as I was reading through, you saw me, I was annotating all of those constraints, trying to figure out what I need to write down. So, okay, company schedules 1 hour for mowing jobs and 3 hours for pruning jobs. So that has to do with hours. This one also has to do with hours, maximum of 9 hours per day. So this first constraint I'm going to write is that one hour for every mowing job plus 3 hours for every pruning job has to be less than or equal to the 9 hours per day max. I also know that P is less than or equal to 2 because it says no more than 2 pruning jobs per day. So I think I've used all the information in the problem. I do have 2 other constraints that I like you to get into the habit of writing. I call them my common sense constraints. And that is that we're not taking negative jobs. P is going to be greater than or equal to 0. M is going to be greater than or equal to 0 because we're not doing negative jobs for our work crews. So those look like my constraints, and then my objective function, f of m comma p, f of my 2 variables. So what am I trying to do? I'm trying to figure out how to maximize the income. So how do I calculate my income? Well, it looks like 40 for every mowing job plus 120 for every pruning shrubbery job. So that's what I will use in my table. I want you to take your 4 constraints, pause the video, put them into slope-intercept form. If they're not, I want you to try graphing them. See if you can shade where the feasible region should be. I'm going to do the same with my paused video, and then we'll both hit play and we'll make sure that our feasible regions look the same before we find vertices and start plugging into the table. So pause the video, start working on this one, and we'll see where we get. All right, so here we are. I'm back. I've kind of graphed all 4 of our constraints, as you can see. The red one I put in slope-intercept form, and some of you, maybe one natural question is, wait, I don't have X and Y. What should be my Y axis? The truth is it doesn't matter. I typically will just make my Y axis the second letter alphabetically, because that's how we do it, X comma Y. And so I made mine M be like my X axis and P be my Y axis, but you would have gotten, the graph might look different, but your end answer would be the same even if you switched those. But since I made P my y-axis, I went ahead and got P by itself to get it in slope-intercept form. So P is less than or equal to negative 1/3 M plus 3. You can see that red line. I put arrows down saying I need to shade below. My two common senses, excuse me. My 2, P is less than or equal to 2, P is greater than or equal to 0. I made those both blue. And so those are constant functions. They're like y equals. So you can see my two blue lines on the graph, horizontal, shading below the 2, 1, shading above the 0, 1. And then my other common sense function I made kind of magenta, m has to be greater than or equal to 0, which kind of restricts us, my common sense ones, to this first quadrant, because we're only dealing with positive numbers of jobs, which makes sense in this real world situation. So here's my feasible region. And so I need to figure out where are these vertices. So it looks like 0, 0 is a vertex. It looks like 0, 2 is a vertex. 1, 2, 3, 4, 5, 6, 2. And then this last one, you'll need to do this sometimes. You start drawing lines and they don't meet, you haven't extended them out far enough. So I'm going to try to maybe grab my ruler because I need it to be a little bit precise so I can see exactly where they're going to hit. So that looks pretty good. And it looks like these will hit right around 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 maybe. So guys, as I'm looking at this, yeah, I'm realizing that my counting has taken a serious hit today. I'm not doing well at all. You guys might have spotted again. I did exactly the same thing. I screwed up my counting. My red line, p is less than or equal to -1/3 m plus 3. Y-intercept should have been 3, and look where I put it. I put it at +4. So let me correct that really quickly. Again, counting, man, I gotta work on that. So let me try to erase all of this because that obviously will affect my vertices and my feasible region. So got that. And I was hoping that wouldn't happen. So I'm going to say that wasn't the point. 1, 2, 3. This is my y-intercept down 1/3. So I will try to definitely do a better job of counting and making sure these examples are right the first time. I do apologize because I know that can make it kind of hard when we're jerked around like this. But it also, I guess, on the plus side, shows that, yeah, when we make mistakes, we can just pick ourselves up and erase it and redo it. So now there's my feasible region. That's looking a little bit better, more like what I was expecting. 0, 2 was the same, 0, 0 was the same. This is now 3, 2. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. Okay. So now that I counted my y-intercept correctly and got it on the graph correctly, again, this is a big, nope, that wasn't my y-intercept. Now let's start plugging our vertices in. So I've got 0, 0, I've got 0, 2, I've got 3, 2, and I've got 9, 0. So when I'm doing this, I like to think about what does this mean? Well, what we're saying in this first row is that it's possible, based on the constraints, for our work crews to work 0 mowing jobs and 0 shrubbery jobs. And that would land us a total of $0 for the day. And that actually makes a lot of sense. That's how the world works. We're not getting paid for work we're not doing. So now let's try this second vertex. So we've got 0 mowing jobs, but we do have 2 pruning shrubbery. So 2 times 120, it looks like that'll get us $240 for that work crew. Not bad. Let's see if we can top it. 40 times our M coordinate plus 120 times our Y coordinate. And we're plugging in 3 and 2. So 3 times 40, that's 120 plus 240. That one looks like it gets us $360 for that kind of job configuration. That's looking good. Let's do one more just to see if we can make even more money, because that is kind of the point of their business. And so when we plug in 9 mowing jobs and 0 pruning shrubbery jobs. And maybe I need to pull this out, but 40 times 9 and then plus 0. So it looks like that one is also 360. So the question was, find a combination of mowing and pruning jobs that will maximize the income. What this is telling us is that we have a tie. This company's work crews should either do 3 mowing jobs and 2 pruning. That would be a winning combination, or 9 mowing, 0 pruning would also bring home the exact same dollar amount, 360, based on those prices and based on those constraints. So guys, real world example, how we can write our variables, write our constraints, graph it, hopefully graph it correctly. That's why I need you guys here to correct me when I start drawing dots at 4 when it should be at 3. But find those vertices, plug them into the table. Same idea with linear programming. We do have some practice problems with this, but it's kind of nice because it takes everything we talked about, graphing lines and shading and finding the intersection. We might have to use substitution elimination if it's not a very nice point where they intersect. But hopefully this helps with 3.4, seeing a few examples. If you have questions, definitely bring them to me so that we can discuss them next time we meet. And otherwise, I will see you next time.